Hi, so as said, I'm Brian, I break things, and I'm actually here today for two very basic reasons. Number one is I had the chance to do a few pen tests on LoRa base stations something like 4 years ago. Sadly, customer project, so I'm not allowed to talk about it and share any details. But let's just say I wasn't very impressed by base stations using protocols like IEC 103, basically old SCADA protocols for transferring LoRa data. And, stuff like using a USB stick with an update.sh that is simply executed with root when you insert it. Stuff like that doesn't really give you a very good impression of LoRa equipment. And the other part is, one of the main lines in the title, Day-1 with the TTIG-868. Simply the question of what are you actually able to achieve in a single day when testing a device. And basis for that is, single day, security is expensive, security is hard. And those are, these basic excuses that a lot of companies make why they can't test their devices. And, why they just roll out crap that's untested, insecure, and nobody ever had a look at. A very nice reference here is, while the British Parliament is actually currently preparing the prequel to the Hunger Games, other parts of the government are actually doing rather good jobs. So the Department for Digital Culture, Media and Sport actually published a code of practice for basic IoT devices last year. Sadly, this code of practice got a little bit of bad feedback from the public, simply due to the fact that many people called it too simple. These are the basic 13 requirements that they want. Stuff like no default passwords, what do we have? Make systems resilient to outage, ensure that personal data is protected, really the very basics of IT security. And in my opinion, these are actually more important than quite a lot of, let's say, exploitation prevention and stuff like that. Simply due to the fact that with all these IoT devices that we have out there, it's more important to ensure that these devices aren't insecure rather than making sure that they're actually secure. All these webcams and other IoT devices that were taken down by the Mirai botnet 3-4 years ago, they had telnet ports that were exposed via UPnP into the internet. That's not a question of being a vulnerability. That's a question of being really stupid and breaking, anything that, everybody would know. I heard it from a lawyer a few years ago, this term of what is gross negligence. And his definition was gross negligence is if your grandmother would have known better. And now, 2019, a grandmother should know better than exposing telnet to the internet, especially with hard-coded credentials. And that's, one of these motivations why I had a look at this device. So, to-do list for my day was a basic security analysis. Look at everything that's there, look at the interfaces, break it open, look at all the parts, but also questions like, actually look at the manual of a device. Because it's always interesting if you have security measures that are available on a device, but nobody tells you how to configure them. So obviously nobody will ever do that. And also stuff like if you have default credentials, there are modern devices that enforce you to change the credentials when setting the device up for the first time. Whereas others, it's like, keep the credentials and it'll still work. So, equipment that I used, I'd say a basic hardware lab. Basically the same equipment as the guys at the Hardware Pwn and the Hardware CTF have. Basically, most of it is cheap stuff, stuff like the logic analyzer. You can go for an expensive Zalea. They're really good. They also have offers for researchers, basically cutting the price in half if you don't do it for profit. But otherwise, take something like a $10 logic analyzer from China. It will do the job. So basic equipment to do something like this is maybe $100, $200, depending on how deep you want to go. So the device, it's this little white box. They cost, I think, between 70 and 85 euros, depending on where you get them. TTIG is the Things Industries LoRaWAN indoor gateway. They came out sometime beginning of this year on a LoRa developer conference. Then they vanished from the market. Then basically around the time of the CFP, they were all over the websites of RS Online, companies like that, the basic distributors, saying, hey, they will be available something like end of June, beginning of July. So I submitted, said, hey, the device is coming out. I'll have a look at it as soon as it's there. I don't really want to wait with the results. Then I got something like 4 or 5 emails shifting the release dates. I think the latest was end of October, so actually after the conference. But luckily, eventually they did actually start sending them out in August. So there was a chance to have a look at it. So interesting parts, it's made for home users. The idea is that somebody buys it, hooks it up to their own Wi-Fi network, and then starts routing LoRa packages everywhere. And it's, I think, the first base station that uses Semtech's new basic station concept. So they set up a new set of protocols, update mechanisms, transport mechanisms for basically the whole LoRa network. So, I hope most of you have heard the term LoRaWAN or LoRa itself. It's a concept for long-range radio communication with low power, meaning that quite a few of the LoRa base stations will have a range of maybe something like 10 to 20 kilometers and are really intended for use with cheap sensors, cheap as in, single-digit dollar areas. And these devices will be able to run off batteries for months or years, depending on how they're made. There have been a few talks on the topic already, mainly aimed at reverse engineering the actual LoRa PHY, due to the fact that the LoRa PHY chip is actually closed source. Meaning what you do is you buy the LoRa module, insert it into your device, and it just does what it does. Which obviously the security community didn't really like, so they started breaking it and had a deeper look at it. So, first steps. The device runs from USB-C. So I thought, hey, USB interface, going to be fun. Sadly, the USB interface was dead. It only uses it for power. You use the setup button. It goes into Wi-Fi access point mode. Then you connect to the network. It actually has a unique Wi-Fi password for WPA2 that is printed onto the device. So it doesn't look as if it was derived from the MAC address or anything. So not really a big chance for drive-by attacks. When you look at it, you've got a little bit of information on the device, which looked a little bit sad. I'm not really a big fan of productive devices that has something like this in the version name, debug. And especially the firmware build date of December 2018. You'd expect that if you've got a device like this that was published during a developer conference, which was, I think, in February 2019, that there'd be feedback from developers and they'd then, bring something back in the firmware, do some optimizations and change stuff. But obviously they didn't manage to write a single firmware update between July and, last December. Little bit sad. The basic interface that we have is already on the previous slide. So you see all the Wi-Fi networks that are around you. You can do basic configuration, set up a few things. It's all done by, simple JSON information or JSON format information that comes out of the device. The only input field that you actually have is the add button, which opens the dialog to add a new Wi-Fi network. Then you can enter the name of a Wi-Fi network and the password. So that's basically the whole attack surface that you have, which sounds a little bit boring, but still fails a little bit. So they actually don't really have any input validation in the BSSID, meaning that also if you go in and you actually set up a Wi-Fi network with XSS in the BSSID and broadcast it, the device will fall for it. So, from the basic input validation, they failed at least a little bit. Port scan. Point number one, it's a very stupid idea to port scan an ESP because they really don't like it, and you have to scan very slowly, but it will still crash no matter how slow you are. This basically is the part that, depending on how many ports are open, how many services are listening, you might not be able to fit into a single day, simply because of crashing the device too often. Turns out the configuration interface is, well, cheap and simple. It's only got port 80 open, so not a problem at all. Then we have the basic station concept. So, as said, it's a completely new concept for configuring these LoRa base stations. Before, from the devices that I pen tested, quite a lot of the stuff was actually configured via SSH in configuration files, meaning somebody actually had to touch the device, configure it, and then the payload communication went out via old SCADA protocols, which never is a good idea nowadays. So Semtech basically developed this protocol being based on JSON using HTTP or other web services, and drew this little, well, sketch of a basic station. So we have eventually a CUP server, which is there for configuration. We have the LNS service, which is there for the actual payload data. And the part that I've got lying here is the part on the left here, which is actually the base station with an SPI interface to the LoRa concentrator. So the first protocol that we have, CUPS, not the printer protocol, is actually the configuration and update server. JSON-based, it's used to fetch basically all configuration that the base station would need. So when you unpack one of these, there's a hard-coded fallback server encoded in there, which is a web service by Semtech themselves. So the device will call home, will transmit its the MAC address, the device ID, the model, and a little bit of the internal configuration. And then it just gets back a big JSON blob with all the necessary information that it needs. So we can already see that there is some sort of credentials that are being transmitted. There actually is a signature for the update, so they did do their homework. Basic length information, which obviously makes, buffer overflows and stuff like that a little bit harder. They actually thought about what the update package would look like. And the interesting parts then are the CUPS URI, so the next server that the device will connect to fetch update information, and the TC URI, which is the URI for the actual payload server, which then is CUP security, authentication. They have 4 options. Sadly, there yet again is an option for no authentication. My problem with stuff like that is my experience from, let's say, large corporate networks always is when they set up a certain system and there's an option for no authentication, no encryption, they will use it for debugging. And then the whole system will work. And at some point, somebody will come by and say, hey, tomorrow's the go live date. Are you ready? And they say, yeah, everything's working. We've just got to switch on security. Which obviously, never works. So I can fully understand that there always are options for no authentication, no encryption, but, there's a certain risk of just offering this option. The way then the authentication works is they've got configuration files on the file system, which are .trust files, which is basically a certificate, which is used for the TLS server authentication. Sorry. Then you have the option of having a client certificate, which will be in a key file. So they're actually using the options of OpenSSL to properly secure the communication channel. And then they have the option of using an authentication token. And the definition there is that you should have a text file which is filled with basic HTTP headers. So the idea really is that into this key file, you write authorization space and then whatever static authorization token that you use. The slightly risky part of this, in this device, I didn't find a way to actually exploit it, but the specification states these few lines. Each authentication mode is configured by providing specific files with credentials being defined by 3 types of files. So the way things work is you don't really activate encryption or the protection mechanisms, but simply by placing the certificate there, the device will find it and use it. Meaning that if an attacker is actually able to delete a file, which via various attack techniques can very often be possible, the attacker might actually be able to disable all these authentication features. Which is, if you have a proper configuration file that actually states, use authentication, if the key is missing, then go into some sort of error state, might have been a slightly better idea in this situation. Then we have the LNS protocol, yet again, completely JSON-based. You've got static paths that are served to on the LNS server. Yet again, the base station goes in, does its authentication, tells the device its serial number, the MAC address and stuff like that. And then the actual LoRa backend tells the base station where to connect to and where to send the payload data. Funnily enough, they also added a feature for a remote shell. Sadly not enabled on the very cheap gateway that I had, but most surely a very interesting research project for future base stations that come out using this project. In general, as said, being JSON, it looks good. They thought about the actual input information that they have. But you've got quite a few rather complex JSON objects that go in. And, for me, it's stuff like this is the radio configuration. Enable is a bool, then you've got an if variable with an int in it. If you have variables like that, somebody who will implement this basic station will have the mistake of actually using data from the JSON model and just pass it into some kind of command line. So this simply is, it makes sense. They thought about how they do it. They chose a good way using JSON, but there are certain risks in future implementations. And, that's very often the problem. You've got one entity creating a protocol, creating some kind of reference implementation, which in certain situations can even be good and secure. And then you've got other companies saying, hey, we can do it better. They don't really understand the actual specifications and then run into quite a few traps. And here the models are really so complex that there is a very big risk of doing something wrong. This then is the moment to jump over to a quick PCAP file. Which we have down here. So this is the basic setup. So the base station comes up, fetches an IP address, initially connects to rjssm.tc, which is the CUP server. Then you can see that it's actually just a very short communication, fetches the configuration data, then goes back into DNS and connects to the Things network, which is basically the operator of these base stations, then establishes the LNS connection and starts, transmitting data, fetching configuration and potential updates. The interesting thing here actually is that you see these nice red lines. Actually, the base station tries to keep the HTTPS connection open as long as possible. At some point, the backend server will say, hey, you've run into your timeout, kills the connection, and the base station simply establishes a new channel. Whereas in other protocols, you've got proper implementations of polling, as in, you send out a request, you keep the channel open as long as possible. I think here the timeout is something like just under a minute, or in some situations, I think it was about 2 minutes. which obviously meaning, establishing a new SSL and HTTPS connection every 2 minutes is quite a lot of unnecessary traffic and unnecessary load. So there might be a little bit of optimization here. Yeah, and then from there on, the communication goes on. As you can see, the basic device uses SSL on all channels. So it's nicely encrypted. Oh, come on. Okay, that was a good trick. I think I just killed my presentation. I'll be back in a second. So the next part then will be having a quick look at the actual SSL and the encrypted channels. So luckily they did really go for proper encryption. Thus I went in, did a little bit of traffic redirection, tried to get into the actual SSL channel, which, let's go back there. Luckily, sadly, depending on how you want to see it, didn't work. When actually looking at the serial console that we'll be getting to a little bit later, you can actually see the information from embed TLS saying, handshake failed. So it's actually a device that has SSL implemented, they're using it, and it does actually function. There are still quite a few of IoT devices out there that do use encrypted channels, but simply don't check the certificates. And this applies both to the CUPS channel, which uses a self-signed certificate, but also to the LNS channel, which does actually use a Let's Encrypt certificate for the backend communication. Port scan, nothing open. So this is then the port scan after having configured the device in client mode. There are no configuration options on the device that can be done by the actual user. So all further configuration comes in via the LNS channel through the SSL tunnel. So quite a good approach. Now it's time for the quick teardown. Device, plastic box, pop off the 2 plastic covers. You've got 2 Torx screws that keep it together. Then you've got a few more clips to remove, and you're in. So the part on the right, you can add a normal plug for the mains to the back and just put it into a normal power socket if you don't want to run it from USB. And the other part is the actual logic. A set based on ESP8266, which I think nowadays is mainly known from the maker scene because they're that cheap, and from quite a few, really cheap Wi-Fi power sockets that usually don't really bring a lot of security with them. It's easy to spot a UART header, which is right here in the middle. As said, the USB interface was disabled, so there wasn't a way of debugging via that, at least initially. And then on the back side, we have the actual LoRa module based on the SX1308, which I didn't have a closer look at. Simply, as said, it's a closed source PHY, and there's already been quite a bit of research on that. So the board that we have, 4 meg flash chip. We've got an I2C port expander simply for the configuration settings and for the buttons. Wi-Fi antenna on board, the LoRa antenna as a small metal antenna. And interestingly, there was actually a USB to UART adapter on there. And it's strange if you've got a dead USB port, but you still have this. I think the chip still costs something like just over €2, so it's not really a that cheap part. Looking into that a little bit deeper. No, sorry. UART first. The RX pin is sadly down, so there's no way of actually inputting information into there. Basically, you have, when it comes up, you've got the whole system configuration. You can see the certificate validation. You see all the information of the stored keys on there. Sadly, they only tell you the signature of the keys. They don't show you the actual content. So yet again, although it's a debug build, it's not really the worst debug build that there could be. And yeah, it prints out basic status information. You know, every time it connects to the server, when it transmits data, gives you RSSI information on the radio interface, and quite a lot of debug information. So, the USB chip. I'm just calling it a few mistakes. So, the USB chip is there, it's properly connected. They actually just had, 2 small mistakes on it. So, what they did was, they've got a ground pin, and there's a resistor on the ground pin that is missing, meaning the chip can't power up due to lacking ground. Add a little piece of wire, ground comes up, and you can start, and, well, it should work. That's what I thought. Connected it, the chip came up, it powered up. Sadly, still no information on the USB interface. Then I had a little bit had a further look. There's a not reset pin, meaning you've got to pull that pin up to VCC so that the chip actually works. What they did was, they had down here, they've got a resistor. This is the reset line. The resistor is connected to ground with a 10K resistor. There nicely is a footprint that goes up to VCC. The data sheet recommends using a 1K resistor for that connection, but the 10K worked just as good. You know, take off the resistor, replace it on the other spot, pull it up to VCC, and you've got debugging via USB. Which basically is a very quick and easy hack to do proper debugging on the device, if you don't really want to have it open the whole time. Then we have the flash memory. That was a very sad research time that I fought with a little bit. So my usual approach with a SPI flash memory is use a Zoid clip, attach it, use the logic analyzer to do a complete SPI trace, and then use sniff from to reconstruct an actual image of the memory, which always works. In this case, it didn't. You know, I was watching all the information on the logic analyzer. Everything worked. I saw basic data reads, but the device didn't come up anymore. And the power LED simply slightly glimmed, and that was sadly it. So I hooked up the scope, had another look, gave it another shot, and it sadly still didn't work. So this is actually a situation that I know from quite a lot of these cheap Chinese logic analyzers. With a logic analyzer, when you read the data, you usually want an infinite input resistance, meaning that you don't draw any current from the device. And usually from my experience, the resistance from the Zalea logic analyzers are big enough. Sadly, in this case, seemingly it wasn't. Luckily enough, the ESP8266 datasheet actually states that there's supposed to be a 200R resistor in line with all the SPI pins. So quick approach, remove the resistor, put in a piece of wire, it still works, meaning you've got a little bit of more current available, and then actually sniffing the data line also works again. That gave me a very nice trace. Well, sadly, the way the ESP8266 works, it actually runs the SPI flash in quad SPI mode, so it's not quite as trivial as normal SPI. Sadly, at this point, my quad SPI decoder didn't really do the job. I've still got some work on that to do and to finally publish that script. So I wasn't able to dump the firmware. But we've got one very good thing here. Semtech actually published the basic C code that they have on GitHub. Meaning, instead of actually doing binary analysis, we can do some source code analysis. Makes life easier for us in this situation. No. Come on. So much for that. So we've got the basic C code for the base station. They also published a set of Python files that will actually allow you to emulate the whole basic station backend. So the CUP server and the LNS server. Meaning that for research purposes, you can really set up the whole thing, do proper fuzzing, and you can also have a certain insight into how the libraries that do the code parsing in the backend work. Due to my approach that I actually wanted to do most of the analysis in a single day, it sadly was a bit too much code to actually read it all by hand. So what I went for is the lame code analysis. I used a cheap Python tool called Flaw Finder, which it doesn't do any magic. It's basically a set of strings that it uses to, search the files with typical bad functions, forbidden functions, and potential insecure implementations. On the right, you can see some of the output. Then quite a lot of it, yet again, is manual work. Usually you've got this approach of saying something like string copy is bad to use. The problem with string copy, not necessarily string copy itself, but the people who are using it. You need proper input validation before calling the actual string copy command. Flaw Finder will only tell you string copy is used, string copy is bad, but isn't able to actually comprehend the lines of code in front of it. So that yet again is manual code analysis. I think I had a manual look at something like 40 or 50 of the issues, just to get a nice overview of it. And it looks as if the developers did actually really do a good job there. So whenever you've got a string copy or a mem copy, they do actually validate the lengths of the input values, make sure that the output targets are long enough. And I actually wasn't able to find a single buffer overflow there. Sad, but yet again, good for the project or for the product. Then, slowly but surely coming to an end. Initially, I talked about what the US government has put together. So for the TTIG-868, this quick verdict. No default passwords. Well, there is the default password for the Wi-Fi, but it's unique, and actually that's the only way of, telling the customer the Wi-Fi password. It has to be hard-coded in some way, so not really a big issue. Vulnerability disclosure policy, no idea. Didn't look at it. Keep software updated. They've got a mechanism for that, so that's a good approach at least, and the mechanism actually also is encrypted, and they've got signatures for it. Securely store credentials. Well, one of the problems with the ESP8266, in contrast to the ESP32, is the fact that it has absolutely no internal memory, meaning that all information that you have has to be stored externally. So even if the flash chip was encrypted, the encryption key would be lying exactly next to it. So there's no real and no proper way of actually protecting the data in there. So we'll guess not. Communicating securely, that's something that they do. Minimize exposed attack surface. Only the configuration port open in host mode or in access point mode, and no configuration or no ports open afterwards. That's perfect. Ensure software integrity. They've got the mechanisms. Ensure that personal data is protected. Hard to say in this situation. I didn't look at the backend. Resilience, make systems resilient to outages, was out of scope. The telemetry data, backend, so I didn't have a look at it. Make it easy for customers to delete personal data. The reset button on the device does actually wipe parts of the memory, so that's a good approach. Whereas there are a few devices, I think my favorite devices were a range of Cisco Soho routers, where you actually, when you went into the factory reset, it simply reset the interface, but left the credentials on the device. So, it basically had a Wi-Fi configuration under the Wi-Fi name, but didn't delete that file. So that at least looks different here. Installation and maintenance are easy. Input data isn't yet validated perfectly. Stuff like the XSS via the BSSID isn't really the nicest things. And as said, parts of the protocol are so complex that they're actually hard to do. So summary is, the device isn't insecure. Not saying that it's a good device, that it's properly done, but at least it isn't broken, which for many IoT devices should be a baseline that we actually have to apply. Configuration Wi-Fi is done nicely. It shuts down after 15 minutes. So you don't have the situation of various, can't remember the brand, there was an IoT coffee machine in the UK a few years back, that if you didn't configure it, it basically left the configuration Wi-Fi open infinitely, meaning that people going by were able to cook coffee within the guy's place, which, can be slightly risky. The basic station protocol is nicely done. They followed security best practices. Still, parsing is a little thing that they've got to optimize. I honestly didn't do it all in a single day. I sadly have a day job, so I basically do this stuff at night and in my free time. I'd say eventually I spent something like 10 hours on the whole thing. So, that's 10 hours of a security professional should be something that every company can afford when actually putting a device onto the market. And as you've seen, I didn't go really deep, but at least I checked for all potential stupid mistakes. And that's something that quite a few companies are lacking. So with that, the outlook, I'll be fixing my quad spy decoder, which is a nice Python script, and I'm hoping to publish that in a few weeks. I've got to give a bunch of other IoT devices a similar run. And I'd actually like to have some feedback on, something like a basic security testing methodology, a defined way of testing an IoT device in, say, something like 3 to 4 hours. A proper checklist, a defined test bench that simply makes it possible when a device comes onto the market, throw it into the lab, give it a quick spin, and then at least be able to give it a thumbs up or a thumbs down. Similar to what the UK has done with these basic security policies. Maybe see if we can spread something like that within the EU or get it to other countries too. With that, thanks for your time, and thanks.
Who has the first question for Brian? No questions.
Perfect.
Thank you, Brian.
There's one hand coming up in the back.
Hey, thanks for the talk. So I was wondering, so IoT devices, slowly they are also adding firmware encryption, meaning that it will be a lot more difficult to start with, actually. How do you look at that? Is it a good practice?
It always depends. So I know it from one pen test where basically one of their main assets was the stuff that was stored on the internal memory. So they encrypted everything, but they actually wanted to save 10 cents. So they used the NXP controller that didn't include any internal memory. So they had the encryption key on the same memory as the encrypted data. So now there are companies going that direction, but not doing it properly. From my perspective, it always highly depends. On the one side, we want the option to actually be able to audit stuff. The classical discussion between Android versus iOS. Android, we can look into it, but it's so big that, not a lot of people do it. Whereas iOS, simply nobody can look into it, and the ones that do find loads of bugs. So in my opinion, it's important to at least do the encryption for user data, customer data, and the actual assets. Quite a lot of IoT devices do create certain amounts of user profiles. They obviously have to be encrypted in a secure way so that even, this device, if it doesn't work anymore, it'll go into the dustbin with all the information that's on it, because when it's broken, I'm not able to wipe it. So the device itself has to protect all customer assets that are on the device, including potentially my Wi-Fi credentials, even when it's broken. So for that part, that's something that's really necessary. with the other parts, encrypted firmware, I think most of the companies are basically doing it because it sounds good, but not really because it's necessary. And obviously, we as a community always need the possibility to do certain amounts of audits. So I think there will have to be a certain compromise. Then, thanks a lot, and I think enjoy lunch.
Yeah, it's lunch break, yeah. Thank you. Thanks.
Thanks.